In this series of basic algebra, today we are going to discuss quadratic function px. A quadratic polynomial ax square plus bx plus c, where a, b, c are real numbers but a is not equal to 0, when denoted by px, it is called a quadratic function because for every real number x, we have a unique real value of px, and when we equate px equals 0, what we get is a quadratic equation. So here ax square plus bx plus c equals 0 is a quadratic equation. This quadratic equation is satisfied by at most two real values of x, which are known as roots or solutions of this quadratic equation. So we will understand this and more about quadratic function and quadratic equation. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. What is meant by 0 of a quadratic polynomial or a quadratic function? Consider px equals 2x square plus x minus 15. For x equals minus 3, p minus 3 will be, which is, so p minus 3 is 0, which implies minus 3 is 0 of 2x square plus x minus 15. Similarly, when x is 5 upon 2, p 5 upon 2 will be, which is, so we get p 5 upon 2 0, which implies 5 upon 2 is a 0 of 2x square plus x minus 15. So for 2x square plus x minus 15, minus 3 and 5 upon 2 are two values of x for which px is 0, and these values of x are called zeros of quadratic polynomial, and every quadratic polynomial has at most two zeros because of degree 2 of quadratic polynomial px. If we equate quadratic function 2x square plus x minus 15 to 0, we get a quadratic equation QE. We can solve this quadratic equation by factorizing the quadratic polynomial 2x square plus x minus 15. We write this middle term x as 6x minus 5x and write four terms as, this is what we call splitting the middle term. In this group of first two terms, we write 2x as common factor multiplied by x plus 3, and in the group of third and fourth term, we write 5 as the common factor into x plus 3 equals 0. Here we have x plus 3 as a common factor, so we write x plus 3 multiplied by 2x minus 5 equals 0. When product of two numbers is 0, then either of them is 0. So x plus 3 is 0 or 2x minus 5 is 0. Solving this linear equations, we get x equals minus 3 or 2x equals 5, x equals 5 upon 2. Now minus 3 and 5 upon 2 are two such values of x for which quadratic polynomial 2x square plus x minus 15 becomes 0. Hence, we call minus 3 and 5 upon 2 as the roots of this quadratic equation. The roots are denoted by alpha and beta. So here alpha is minus 3 and beta 5 upon 2. These two values are also known as solution of quadratic equation QE 2x square plus x minus 15 equals 0. We will consider a reverse situation in which suppose we are given two roots of a quadratic equation, then are we able to find the quadratic equation? Suppose these given roots are same as these two, alpha equals minus 3, beta equals 5 upon 2. If we consider this expression, then from this expression if we write x minus alpha multiplied by x minus beta equals 0, that is x minus minus 3 into x minus 5 upon 2 equals 0, then we get x plus 3 multiplied by x minus 5 upon 2 equals 0. That will be x square plus 3 minus 5 upon 2 into x plus 3 into minus 5 upon 2 equals 0. That will be x square half x minus 15 upon 2 equals 0. Now multiplying throughout by 2, we will get the original quadratic equation 2x square plus x minus 15 equals 0. So by using x minus alpha into x minus beta equals 0, we can construct quadratic equation from the given roots alpha and beta. How to construct a quadratic equation if the given roots are 7 and minus 3? Here alpha is 7 and beta minus 3. Required quadratic equation will be x minus alpha into x minus beta equals 0, x minus 7 into x plus 3 equals 0. That will be x square plus minus 7 plus 3 x plus minus 7 into 3 equals 0. That will be x square minus 4x minus 21 equals 0, which is required quadratic equation. For direct forming the quadratic equation, we write x square plus alpha plus beta into x plus alpha beta equals 0, which is x square plus 7 minus 3 x plus 7 into minus 3 equals 0, which is x square plus 4x minus 21 equals 0. Same as this. Quadratic formula for a standard quadratic equation ax square plus bx plus c equals 0, we can have quadratic formula which gives directly two roots of this quadratic equation from the values of a, b and c. So let us write derivation of quadratic formula QF. We have quadratic equation. We will divide throughout by this a to make coefficient of x square 1. So it will be x square plus b upon a x plus c upon a equals 0. We write this as x square plus b upon a x equals minus c upon a. We will make this left hand side a perfect square quadratic polynomial by adding square of minus half of coefficient of the middle term x, that is p upon a, which is p square upon 4a square. So this expression reduces to x square plus b upon ax plus b square upon 4a square equals minus c upon a plus b square upon 4a square. Now we write this perfect square polynomial as square root of x square x plus square root of b square upon 4a square b upon 2a whole square equals minus 4ac plus b square upon 4a square. Now taking square root on both sides, we get x plus b upon 2a equals plus minus square root this b square minus 4ac upon 2a, that will be x equals minus b upon 2a plus minus square root b square minus 4ac upon 2a. So finally we get quadratic formula x equals minus b plus minus b square minus 4ac upon 2a. This formula gives us two roots of this quadratic equation. For a standard quadratic equation, we have just derived a quadratic formula x equals minus b plus minus square root b square minus 4ac upon 2a, which gives us two roots of this quadratic equation. Let us denote the two roots by alpha and beta, which will be alpha equals minus b plus square root b square minus 4ac upon 2a, and beta will be minus b minus square root b square minus 4ac upon 2a. Here sum of two roots SOR will be alpha plus beta, that will be root b square minus 4ac minus root b square minus 4ac. This will be minus 2b upon 2a or minus b upon a, and product of two roots POR will be alpha into beta minus b whole square b square minus b square minus 4ac upon 4a square, which will be b square minus b square 0, 4ac upon 4a square, this will be c upon a. So we get two important results. Sum of roots alpha plus beta is minus b upon a, and product of roots alpha beta equals c upon a. These are two important results which will help us a great deal while solving problems. Discriminant and nature of root. In the quadratic formula, the quantity within the radical sign or square root b square minus 4ac plays an important role in deciding nature of root. Nature of root means whether it will be real and distinct, whether it will be equal, or whether non-real or imaginary. The quantity b square minus 4ac, denoted by d or delta, is referred to as discriminant, and since sits within the radical sign, if d is positive, roots will be real and distinct. If d is 0, roots will be equal, and if d is negative, then roots will be non-real or imaginary. By knowing discriminant, we can decide nature of root of a quadratic equation. Let us see how. A quadratic polynomial has one of its zeros is 1 plus root 5, and it satisfies p1 equals 2. We have to find the quadratic polynomial. If one zero of the required quadratic polynomial is 1 plus root 5, then the second zero will be conjugate of the first one, that is 1 minus root 5. Therefore, if alpha is 1 plus root 5, beta will be 1 minus root 5, and the required quadratic polynomial px will be k times x square minus alpha plus beta x plus alpha beta. Now from here, alpha plus beta will be 2, and alpha beta 1 minus 5 minus 4. So px will be k times x square minus 2x minus 4. But it is given that p1 equals 2. So we have p1 equals k into 1 square minus 2 into 1 minus 4 equals 2. So k into 1 minus 6, 2, or k equals minus 2 upon 5. So the required quadratic polynomial from here will be px equals minus 2 upon 5 x square minus 2x minus 4. If one root of quadratic polynomial k into x minus 1 whole square equals 5x minus 7 is double the other root, that means if one root is alpha, the other root will be 2 alpha, and we have to show that k is 2 or minus 25. Given quadratic equation is, which is or this will be kx square minus 2k plus 5 x plus k plus 7 equals 0. Comparing this with standard quadratic equation, we get a equals k, b equals minus 2k plus 5 and c k plus 7. Now sum of two roots SOR will be alpha plus 2 alpha from here, which is minus b upon a 2k plus 5 upon k. So 3 alpha will be 2k plus 5 upon k. Alpha will be 2k plus 5 upon 3k. This will be the first root. Now product of two roots alpha into 2 alpha. 2 alpha square will be c upon a. So 2 into 2k plus 5 whole square upon 9k square will be c, which is k plus 7 upon a k. This will be 2 upon 9 into 4k square plus 20k plus 25 upon, cancelling 1k here, k equals k plus 7. So that will be 2 into 4k square plus 20k plus 25 equals 9k into k plus 7. This will be or k square plus 23k minus 50 equals 0. That is k plus 25 into k minus 2 equals 0. That gives k equals minus 25 or k equals 2, like we have to show here. If one root of quadratic polynomial k into x minus 1 whole square equals 5x minus 7 is double the other root, that means if one root is alpha, the other root will be 2 alpha, and we have to show that k is 2 or minus 25. Given quadratic equation is, which is or this will be kx square minus 2k plus 5 x plus k plus 7 equals 0. Comparing this with standard quadratic equation, we get a equals k, b equals minus 2k plus 5 and c k plus 7. Now sum of two roots SOR will be alpha plus 2 alpha from here, which is minus b upon a 2k plus 5 upon k. So 3 alpha will be 2k plus 5 upon k. Alpha will be 2k plus 5 upon 3k. This will be the first root. Now product of two roots alpha into 2 alpha. 2 alpha square will be c upon a. So 2 into 2k plus 5 whole square upon 9k square will be c, which is k plus 7 upon a k. This will be 2 upon 9 into 4k square plus 20k plus 25 upon, cancelling 1k here, k equals k plus 7. So that will be 2 into 4k square plus 20k plus 25 equals 9k into k plus 7. This will be or k square plus 23k minus 50 equals 0. That is k plus 25 into k minus 2 equals 0. That gives k equals minus 25 or k equals 2, like we have to show here. If difference of roots of a quadratic equation equals product of roots. We have to show that a equals 2. First we compare the given quadratic equation with the standard equation. That gives a equals 2, b equals minus a plus 1, c equals a minus 1. We have sum of roots alpha plus beta equals minus b upon a, which in this case will be this a plus 1 upon this 2, and product of roots alpha beta will be c upon a, that will be this a minus 1 upon 2. Now it is given that difference of roots equals product of roots, which is alpha minus beta equals alpha beta. Squaring it gives alpha square plus beta square minus 2 alpha beta equals alpha beta square. We will add 4 alpha beta on both sides. That will give us alpha square plus beta square plus 2 alpha beta equals alpha beta square plus 4 alpha beta. That further will be alpha plus beta whole square equals alpha beta square plus 4 alpha beta. Now we will substitute these values for alpha plus beta and alpha beta. That will give us a plus 1 by 2 whole square equals a minus 1 by 2 whole square plus 4 times a minus 1 by 2. This will be plus 2a plus 1 upon 4 equals a square minus 2a plus 1 upon 4 plus 2a minus 2 multiplying throughout by 4 plus 8a minus 8, cancelling a square plus 1 from both sides. This will be 8a minus 4a equals 8, 4a equals 8, a equals 2. This is what we have to prove, a equals 2. We have to find the condition in terms of a, b and c if one of the roots of the quadratic equation ax square plus bx plus c equals 0 is number 1 negative of each other, number 2 one root is thrice the other, and number 3 the roots are reciprocal of each other. Now answering the first question, let one root be alpha, then the other root will be minus alpha. So sum of roots alpha minus alpha will be 0, but this, as we know, is also minus b upon a. So that gives b equals 0. So this is the first condition that we got, b equals 0. Answering the second question, if one root is alpha, the other root will be 3 alpha, and sum of roots will be alpha plus 3 alpha, 4 alpha, which is also minus b upon a, and this implies alpha equals minus b upon 4a. Product of roots alpha into 3 alpha will be 3 alpha square, which is also, as we know, c upon a. Using this value of alpha here, this will be 3 into minus b upon 4a whole square, which equals c upon a, which further will be 3b square upon 16a square equals c upon a. Cancelling a from both sides, we get b square equals 16 upon 3 ac, and this is the second condition that we got. Now answering the third question, if one root is alpha, the other will be 1 upon alpha. Product of roots gives alpha into 1 upon alpha equals 1, which is also, as we know, is c upon a. This gives c equals a, and this is the third condition that we got. Quadratic equations x square minus ax plus b equals 0 and x square minus ex plus f equals 0 have one root in common. The second equation has equal roots and AC equals 2 times B plus F. We have to find the condition in terms of A, B, E and F. According to this condition, let alpha be the common root that will satisfy this first quadratic equation. So we can write alpha square minus A alpha plus B equals 0. We name this 1. Now for this first quadratic equation, we have sum of roots minus B upon A, which is A upon 1 A. Product of roots is C upon A, that is B upon 1 B. Now the second equation has equal roots. So for this equation we have sum of roots minus B upon A. So alpha plus alpha equals minus of minus E upon 1, that is E. So this gives 2 alpha equals E or alpha equals E upon 2, and product of roots will be alpha into alpha, alpha square. So C upon A equals F upon 1 equals alpha square. So F is alpha square. Now we will use alpha equals E upon 2 and alpha square equals F in equation 1 to get F minus A times E upon 2 plus B equals 0. AE upon 2 equals B plus F, that is AE equals 2 times B plus F, and this is the required condition in terms of A, B, E and F. We have to find whether the graphs of following functions will intersect the x-axis or not. The first function is y equals x square plus x plus 2. This function will intersect the x-axis if and only if the roots of this function will be real and distinct, for which the discriminant b square minus 4ac must be non-negative. For this given function, b square minus 4ac will be 1 square minus 4, 1 into 2, 1 minus 8, minus 7. Since discriminant is negative, this quadratic function will have no real roots. Obviously, the graph of this function will not intersect the x-axis. Since there is x square term in the function, the nature of this curve will be a parabola opening upwards. We will find its lowermost point. For that, we write this function y equals x square plus x plus 2 as x square plus x plus half square plus 2 minus half square. We have created a quadratic polynomial here, which we write x plus half whole square plus 7 upon 4. This we write y minus 7 upon 4 equals x plus half whole square. Equating both sides to 0, we will get y equals 7 upon 4 and x minus half. So the lowermost point on this curve is minus half comma 7 upon 4. Obviously, this lowermost point is not on the x-axis. Second function is y equals x square minus 3x minus 7. Discriminant d will be b square minus 4ac. 9 plus 28, 37, which is positive, implying roots are real and distinct. Obviously, graph of this function intersect the x-axis. From the presence of x square term, it is clear that the graph will be a parabola opening upwards. For finding the lowermost point on this parabola, we write given function y equals x square minus 3x plus 3 upon 2 whole square minus 7 minus 3 upon 2 whole square. From these first three terms, we write y equals x minus 3 upon 2 whole square minus 7 minus 9 upon 4. That will be y equals x minus 3 upon 2 whole square minus 37 upon 4, or y plus 37 upon 4 equals x minus 3 upon 2 whole square. Equating both sides to 0, we get y equals minus 37 upon 4 and x 3 upon 2. So this lowermost point on this parabola is 3 upon 2 comma minus 37 upon 4. Position of x-axis and y-axis will be somewhat like this. And the third function is y equals x square plus 6x plus 9, which can be factorized as x plus 3 whole square. So y minus 0 equals x plus 3 whole square. Equating both sides to 0, y equals 0 and x equals minus 3. Presence of x square term specifies the shape of the graph to be where the bottommost point will be minus 3, 0 and the x-axis like this. So the graph of the function cuts the x-axis in one point minus 3, 0. This can also be ascertained by finding the discriminant d, which is b square, that is 6 square minus 4ac, giving 0, and by nature of roots, when the discriminant is 0, implies that the equation has real and equal solution minus 3, 0. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. See you in the next video. Until then, keep watching Number Collage. Thank you.